In this video, we are going to discuss question 6.50. A 5 kilogram ball of clay is thrown downward from a height of 3 meters with a speed of 5 meters per second onto a spring with K equal 1600 Newton meter. The clay compresses the spring a certain maximum amount before momentarily stopping. Find the maximum compression of the spring. So question says you have a clay which you drop from a certain height h above the equilibrium position of the spring. So let this be the equilibrium position of my spring. We drop the clay from a height h above the equilibrium position. At this position, the speed of the clay with which it is dropped, I will call that as initial speed, is 5 meters per second. Mass of the clay is 5 kilogram. Spring constant K is 1600 Newton per meter. When the clay is dropped on the spring, it compresses the spring by a maximum amount, delta X. And since it compresses the spring by a maximum amount, at this position, the clay momentarily comes to a stop. And since it comes to a stop, its final velocity, V final, will be equal to 0. Question is asking me to find the maximum compression. So I need to find the value of delta X. We're going to use the law of conservation of energy to solve this problem. Law of conservation of energy says that total mechanical energy at any 2 point in motion is always equal. So let me take those 2 points as my initial point. I will call this 1 and my final point 2. We write according to law of conservation of energy, total energy at 1 should be equal to total mechanical energy at 2. Total mechanical energy is nothing but sum of kinetic plus potential energy. So we will write that for both of the energy values here, K2 plus U2. Kinetic energy at point 1 will be half mv squared because the ball is released with a speed v, and the potential energy will be mgh because the clay ball has been released from a height h above the reference point, above the equilibrium position. Kinetic energy at point 2 will be 0 because velocity at point 2 is 0. The ball momentarily stops at point 2, so my kinetic energy at that point will be 0. Potential energy at point 2 is sum of two potential energy. One is the potential energy of the spring because the spring is compressed. And second is the gravitational potential energy because this is my reference point here. Whether you go above the reference point or you go below the reference point, if you move away from your reference point, you will have gravitational potential energy. So since my ball is below the reference point, it is a distance delta x below the reference point, it will have gravitational potential energy also. So here I will write potential energy at point 2 as half k delta x squared for the spring plus mg minus delta x. We take delta x minus here because this is the case of compression and I am below my reference point. So if you go below the reference point, the displacement must be taken as negative. So we rewrite this expression half mv squared plus mgh equals half k delta x squared minus mg delta x. From this point, I will use shift solve because now I have a quadratic term over here. I have a quadratic term and I have two constant values. So instead of complicating my problem by rearranging the terms and solving them, I will use shift solve at this point. So let us substitute the value of all the quantities given to us and then use shift solve. I will write half. Mass of the ball is 5. Speed of the ball is also 5 plus 5 times 9.81. Height of the ball h is 3 meter. It's given in the question. So 3 equals half. K is 1600. Delta x I don't know. Squared minus 5 times 9.81 into delta x, which I don't know. So put this in the calculator. And if this term is too long, you can solve the individual values over here, club them together, and then you can put them in the calculator. So when I solve for this, I get my delta x as 0.543 meter. So this is the maximum displacement in the spring. If this equation is too big for you to put in the calculator, you can first solve this expression on the left-hand side. And whatever answer you get when you solve this, you can put that answer here equal the rest of the term on the right-hand side. That will make your expression small and easily handled in the calculator to shift solve.